understand the role of feedback in nonlinear systems, right. When there exist closed paths for signal transmission, we say that there is feedback, and in 1975 Freeman said that feedback occurs in almost every part of the nervous system of an animal. So, feedback is very central and fundamental to all systems, right. Let us see through a signal flow graph what this is. So, we have xj of n, there is a feed forward weight w, and we have this yk of n, and we have a unit delay in the feedback, right. This is a closed path in the signal transmission process. This is the closed path, right. There is a loop here. And this is an example of unit delay system, and we have seen this kind of transfer function in literature, right. So, let us analyze this slightly more carefully, but I think before we begin, why do we want to bring in feedback into these systems, right. I did mention to you that Freeman in 1975 he mentioned that feedback occurs in every part of the nervous system of an animal, right. He said that there is feedback in every part of the nervous system of the animal, and do we believe in this theory, right. As we even think about our actions and our inferences, etc., there is definitely a role of feedback, right. For example, I have to make a decision if, as I am grading an answer paper, if I have to make a decision if the candidate is going to pass this exam or not, there is, I go through, it is just not I just grade the paper once and I just stop with the grades. Again I look at the overall performance, there is, I mean, unless it is very bad or very good, or if it is a borderline case, there is again a closed path that I take to figure out what is happening there and then adjust my constants and my thresholds accordingly, right. So, there is feedback when we make a decision process, there is feedback in our thinking, in our memory, in our learning, there is feedback, and this is very central. But with a slight digression what I mentioned, let us get back to the mainstream. So, let us look at the Z transform of ykn. So, this is if you just look at the simplification of the system, there is a feed forward gain which is w, feedback path is z power minus 1. So, you apply your g plus 1 plus gh. So, you have w upon 1 minus w z power minus 1 times the z transform of this input xj n. So, if you can simplify this further, this is w times. So, let us expand this denominator polynomial in terms of a power series. So, this is summation L equals 0 to infinity w power L z power minus L times the z transform of xj of n. So, this can be written in the form summation L equals 0 to infinity w power L plus 1 times the, if you do the inverse Z transform, right, I just take a ykn here and I can write it in one shot. This is x suffix j of n minus L, right. I think what is very important here is just not the Z transforms here, but I think you have to focus on this term here, that you are sampling the input signal x j of n that is delayed L time steps in discrete units of time, and then it is you are scaling this, right. This is very important. That means there is, it is not that the sample at time n is just not dependent on the input at time n, but to different inputs in the past. This is basically feedback, right. Sample of the input signal delayed by L discrete time steps. So, therefore, there is fundamentally a memory here associated, right, because of this this pole that we have here, right. There is fundamentally a memory in the system. Let us look at the following cases. If mod W less than 1, the output signal yk of n is exponentially convergent, right. What I mean is, if you plot yk of n versus time n, right, you can see that it sort of dives exponentially down, right. You have W times xj 0 at time step n equals 0, and time step 1, 2, 3 it starts coming down. Now, there are other cases. If absolute value of W is greater than or equal to 1, then yk of n is divergent, and the system is unstable. And if absolute value of W is equal to 1, we say that the divergence is linear, and if absolute value of W is greater than 1, we say that the divergence is exponential. I mean, if you just sketch them, you can kind of see the analogy here. Just a small sketch. In one case, you have linear divergence, and in the other case you have exponential divergence. Suppose we let the system to have finite memory. This is very important because we can see how this this simplifies. So, Ykn we can approximate this to be W times xj of n plus W square xj of n minus 1 plus dot 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 W power n xj of n minus capital N plus 1. Let us assume that we let it through n capital N time steps, right, and then these are the scales W W square, so on and so forth. So, there is essentially a feedback here. All the neural elements have this feedback, and if you think about finite memory, that means you are only going to combine the inputs up to a certain time step in the past with these associated scale factors, and that is what your output signal is up to this memory, right, and this forms our feedback mechanism, and neural elements have this feedback. And in general, if you think about nonlinear systems, analysis of the dynamics, particularly nonlinear dynamics, is very complicated. And when we think about networks, that is when we think about network architectures where we have recurrence in neural networks, we have these recurrent neural networks where there is feedback mechanism from the output to the input. At that step we can think about architectures as to what is the kind of memory that we want to bring in and how many units of memory we want to bring in, and we can look at these sophistications when we revisit the network architectures. Okay, having discussed the feedback mechanism, neural network representations as digraphs, and the neuronal models, we are sort of ready to understand networks, network architectures, right. The first network architecture is a single layer feed forward network. This is a simplistic thing, single layered feed forward network. And let us see how this is. We have an input layer and we have an output layer of neurons, and we have weights connecting these inputs to the output. This is a fully connected network. So, I am just showing you some connections. You can sort of imagine that all the nodes in the input layer, they are the source nodes, they are all computed, they are all connected to the output neurons. At the source there is no computation. So, these are the source nodes, and these are the output layer of neurons. Here there is no computation because you are just getting the inputs. Here there are these are the synaptic links, you connect them to the output, at the output you do some computations, right. This is simplistic feed forward network. We can kind of generalize the single layer to multiple layered feed forward networks. Let us see how this architecture is. So, the idea is pretty straightforward. So, we start with the source nodes at the input, and I will just mark in red for the hidden layers. We have connections from the source nodes to the first hidden layer and dot dot dot. You can have them fully connected. All the nodes at the inputs are connected to those at the hidden layer, and this goes on and with various connections across the hidden layers, and then from the last hidden layer you can connect to the output layer of the neurons, right, all possible connections. And one thing that you have to note is the multi-layered feed forward network can be A, fully connected, or it can be partially connected, and this has sort of a bearing on the learning, right, because if it is fully connected then it may not be a specialized network, because you can have some generalization ability there, and if it is partially connected it may be a specialized network, because you do not want it to be able to generalize everything. So, depending upon the kind of application that you have in mind in terms of your knowledge representation within the network, you may want it to be fully connected or you may want it to be partially connected. So, here it is a straightforward feed forward network. There is no feedback, there is no closed path from the output to any of the hidden layers or to the input, right. There is no such feedback mechanism, and that is why it is called a feed forward. And there are also no lateral connections between neurons in a particular layer, right. We do not have any lateral connections, we also do not have a feedback from the output to the layers before. So, one can endow feedback into the network, and that leads us into the recurrent network. So, let us understand what recurrent networks are and kind of see the architectural sketch. So, in this example I look at a case where I have a delay and the output signal goes through a delay and then comes back and is fed into the inputs, right. Similarly, I can have another output which can be tapped. I go through a delay so on and so forth. And this network, in this example, there is no self feedback loop, but in principle one can think of having self feedback loops, and the presence of feedback loops has impact on the learning capability of the network, right. And we can generalize this idea, right. We can now from these delays to the outputs, we can have hidden layers and we can connect them and we can form outputs. So, let me sketch this up. So on and so forth, right. So, these are our delays, this is a hidden layer, you can have a stack of hidden layers if you want, and these are the outputs, and then you have a feedback mechanism from the output through the delays to the processing elements in the hidden layers, right. So, this is an example of a recurrent network sketch. Of a recurrent network. So, I think what is very important to realize is there is a feedback mechanism through these delays from the output back to the input, and you can have various connections and various configurations as to where the feedback is present, and that would complicate the network. And this architecture also does not have lateral connections. So, what I mean about lateral connections is if you have connections between these processing elements in the same layer, those are lateral connections, right. And you can have feedback and other things across lateral connections. In general, for a simplistic recurrent network, you do not have lateral connections. I think this is something which is to be made very clear. So, what we missed in this sketch, right, of course, I gave all the connections, but I think what was missing were the inputs, right. I have sketched these in red, and these are the input signals, and you can give the same inputs to all the neurons, and this could be one architecture. You can have portion of the inputs provided to individual neurons, that can be another configuration, right. So, but I think what is important is to have the inputs present at the input layer, and then you can have hidden layers, and then you tap from the outputs and it goes through these delays. So, I think this sort of wraps up on the sketch of the recurrent network, but bear in mind you need not have lateral connections, this is the only difference, but you have inputs, you have these delays, you have the outputs. Okay, we stop here.